Right, so I'm going to do question 9 on the sheet, girls. Question 9 says that you've got a ship A, which is 50 kilometres north of B. So I'm going to put B here at the origin. A's up there, 50 kilometres apart. Ship A is travelling southwest, so it's in this direction. And of course, if it's travelling southwest, that means that this angle here is going to be 45 degrees. And B is travelling due west at 17. Find the magnitude and direction of the velocity of B relative to A. So find VBA, which means I've got to find VB minus VA. So first of all, I'll get them both in their IJ forms. So the velocity of B is travelling just in the I direction, it's along the I axis, but in the negative I axis because it's going west. So that's going to be minus 17 plus 0J. Now VA, you've got to do a bit of work for VA. VA is travelling southwest. What I'm going to do here is draw a right angle triangle around that vector. I'm going to make a right angle triangle. These are the two components. This is the I component and the J component. If that's 45, this angle here also has to be 45. Okay, so the I component, this one here, this is the side that's adjacent to the angle, that red dot angle 45. So this bit will be 24 root 2 by the cos of 45. And this component over here then will be 24 root 2 sine of 45. Okay, so I'm going to write down then my I and J parts of A. So the VA is equal to 24 root 2 cos 45 in the I direction, but it's travelling in the negative I direction because it's heading west. So this will be minus 24 root 2. The cos of 45 is 1 over root 2. Now the J component, again, it's heading in a southerly direction. It's going southwest. So that's going to be minus J axis. And again, it's 24 root 2 sine 45. So that's 24 root 2. And the sine of 45 is 1 over root 2 as well. So that's my I component, that's the J component. And when I tidy that up, it becomes minus 24I minus 24J. Okay, so that's my VA rather. So let's get the VBA. The VBA is therefore equal to minus 17I plus 0J minus the VA, which is minus 24I minus 24J. Okay, and when I sort that out, minus 17 plus 24 will give me 7I, and this is going to become a plus, of course, minus by minus, and I get 24J. Now the question asks for the magnitude and direction, so to find the magnitude of that relative velocity, it will be, remember the relative velocity is in the 7, positive I, positive J direction, so it's heading off in that direction like that. So the actual magnitude of it, remember, will be, that's like making a right angle and doing a Pythagoras, so it would be the square root of 7 squared plus 24 squared. When you work that out, you get 25, and that's kilometres per hour. Now the direction that it's going in, let's do that next. The direction, I'll do that down here, the direction, okay, so here it is, that's the vector. This is the angle that it makes with the I-axis, positive sense of the I-axis, that red dot there. So I'm going to find the value of that angle. So if this is the vector, that blue line there is the vector, and I draw a right angle triangle around it. And I know that what it is, it's 7 on the I, 24 on the J, so this has a value of 7, this has a value of 24. This is my angle, I'll call it alpha. So a tan of alpha is equal to the opposite over the adjacent, 24 over 7. And when you work that out, you get an alpha of 73.74 degrees. Okay, so the direction of that vector is it's heading east and then it's going north. So it's east 73.74 degrees north. Now the next part of the question says, how long can they exchange signals? So we've got these two ships, how long can they exchange signals for? So what's the situation? So look what we have. We have B here, A's 50 kilometres away from it up there. Okay, so what I'm going to do is going to put in the relative velocity line, because that will tell us all about where one is relative to the other. And we have this relative velocity line here, VBA. So I'm going to put that in, and because it's VBA, I'm going to draw it travelling through B, passing through B. Okay, so that's my VBA. I'm going to drop a perpendicular from A down onto it, and it's going to hit that at a right angle. And that dotted line there, that's the closest distance that they can be to each other. So that's D. We'll call that D. And of course we know what this is. This is 50, isn't it? That distance from there to there is 50. I was told that already at the beginning. Okay, so to find D, I'm going to have to use this triangle there. Now, I know what alpha is, but alpha is there, positive sense of the y-axis, which means I'm going to have to get into the triangle. So I'll take this 73.74 from 90, and that will give me that angle there, beta. So then I can find D pretty easily. I can say that D is equal to, well, the sine of beta is D over 50, so D is equal to 50 times the sine of beta. And when I take that angle alpha, 73.74 from 90, I'll get 16.26, and that, when I work it out, will give me a D of 14 kilometres. Okay, so that's the closest they can be. Right, how long can they exchange signals for if it can only happen when they're not more than 20 kilometres apart? Okay, so again, I'm going to draw the situation. I have my relative velocity line, I have that already. I know all about that. I know that A is up here. A is up here. Right, so, and I have this closest distance, D. I know what that is. So what I'm going to do is draw a circle around A with a radius of 20 kilometres, because that's the distance from which they can exchange signals. So remember, that distance from there to there is 50, so it's not going to be as far as there to there. So it's going to be something like this. Sorry about my bit crooked circle there. Anyway, then I'm going to drop a line from A, cutting the circle and the relative velocity line. And then I'm going to draw on the other side the same thing, from A down to the relative velocity line where the circle cuts it. And those two distances, those two blue lines, are corresponding to the 20. That's the area around there from which they can exchange signals. Right, so what I'm after then, I want to find the time from which they can exchange signals. So the time is going to be relative distance divided by relative speed, and I'm stressing relative. So it's all coming, all that information has to come from the relative velocity line, which is the red line. Okay, so I'm just going to lift this triangle. This is the one I'm interested in. So I'm going to lift this triangle here out of there. This is my red line there. Okay, so I do have this distance here, D. So what do I have? I've got D, which is 14 kilometres. I've got 20 for that and 20 for that. I have to find the distance on the red line. These two triangles, of course, are identical. So this unknown side I'll call x, which has to be the same as that, which means that the relative distance is this bit here, 2x, divided by the relative speed, which is the relative speed of your VBA line. That's the magnitude. I already have that. If I do a Pythagoras on this here, 20, 14 and x. So 20 squared, so to find x I'm going to say 20 squared minus 14 squared is equal to x squared. That's using my Pythagoras theorem. That gives me an x of 14.28. Okay, so 2x, I'll double that and I'll put it in here. And when I do that, this will become 2 14.28 divided by the VBA, magnitude of VBA I already have. Remember, I found that over here to be 25. So I'll divide that by 25. And when I do that, I get 1.43. So my time is 1.43. And of course, that's hours. So they can exchange signals for 1.43 hours. If I were to turn that into minutes, just multiply it all by 60, and that will give me 68.55 minutes. So they can exchange signals for 1 hour and nearly 9 minutes. So signal exchange for that long before they're out of reach.